In this lecture, Charles and I will describe how to set up your home computer to run the tools needed to test and evaluate your system Verilog designs. Before that, I need to provide some necessary context. In this course, we'll be using two approaches for testing your system Verilog designs. The first is to use Modelsim, which is an industrial strength behavioral simulator. If you find yourself in a career in hardware design, you'll most likely be using Modelsim extensively in your place of employment, as this is the industrial standard for HDL simulation. Modelsim can simulate your test benches and your designs under test, as I showed in the previous lecture. Modelsim works by compiling your system Verilog code into a binary representation of the set of triggers and associated actions for each trigger that define the behavior of your system Verilog code. The triggers are defined by the signals that you provide in the sensitivity list of your always statements, as well as the signals that are on the right-hand side of your continuous assignment statements. As you might imagine, the inherent weakness of this approach is that any circular relationship between an action and a trigger will cause Modelsim to enter an unrecoverable infinite loop of triggers and actions. So you need to always be careful to avoid this in your design. Modelsim simulation results are shown in a waveform or as printed output messages from your test bench. Modelsim also supports breakpoints, line-by-line debugging, analysis of event chains, and has full support for all the data types in the Verilog, System CSCE, and VHDL standards. You can also simulate Verilog, VHDL, and System CSCE code together in one seamless simulation. The advantage of using Modelsim with your test benches is the freedom to test any individual module that comprises your design at any level of the design hierarchy. For example, when designing your CPU, you can separately test your ALU, your register file, and then eventually your whole CPU as you move from the bottom of the design hierarchy toward the root, and the root is typically the component that you would be shipping to customers. It's the most abstract component. This approach allows your design under test to have any inputs and outputs, since you would write a custom test bench for each of your designs under test. The second testing approach we'll use in this class is to run your design on a virtual version of the prototyping board that we previously used in the lab-based version of this class. The board is called the DE2-115, which is a roughly 12-inch by 12-inch printed circuit board that connects an FPGA, a field programmable gate array, to a set of external devices, such as switches, buttons, LEDs, 7-segment displays, parallel and serial ports, DRAM, SRAM, flash RAM, SD card slot, chipsets for LCD, VGA, USB, audio, Ethernet, and infrared communication. An FPGA, or a field programmable gate array, is an electronically programmable device that will behave as any arbitrary logic circuit you synthesize and program onto the FPGA. FPGAs allow you to realize your designs as physical hardware with which you can physically interact. It's kind of like you building real hardware. But since we can't work with the physical DE2-115 boards, we're going to be using a virtual DE2-115 board. The virtual board was developed by Charles using fully customized code that he wrote from scratch. The virtual DE2-115 does not use Modelsim. Instead, it's based on a separate tool, another tool called Verilator, which is a compiler that merges the behavior defined in arbitrary system Verilog code with a customized simulator. So it combines your system Verilog with its own simulator. and integrates them together into one blob as a C program that can be compiled and run as a software library. This makes it really easy to write other programs, other software that interact with the simulated behavior of your system Verilog. The virtual DE2 115 adds in software that create a graphical user interface that Charles developed in Golang, as well as a set of makefiles that links the output of Verilator with the graphical software that Charles wrote that creates a graphical virtual DE2 on your screen. The main drawback of Verilator is that it does not support the data types that are required by the System Verilog standard. Specifically, it doesn't understand concepts such as unknown, undefined, don't care, contention, or high impedance values, which, as I described before, are encoded as the X and the 0 states of the logic type that we're using in the course. The advantage of using the virtual DE2 115 board is that it provides a virtual version of the switches, buttons, LEDs, and 7-segment displays that you would normally be interacting with on the physical DE2 board if we had been teaching the lab-based version of the class. Our virtual DE2 115 currently lacks support for the other features I mentioned on the physical DE2 115 board, such as VGA audio and networking, but these are features that we hope to add to the software in the future as we further refine the code. The virtual board has a graphical front end that displays the state of the outputs graphically on your screen and allows you to use your mouse to manipulate the inputs, which in this case are switches and buttons. However, simulating with Modelsim and simulating on the virtual DE2 115 use different methodologies. So using the virtual DE2 115 forces you, as a designer, to adhere to the conventions that are normally required when performing physical design. Specifically, what I mean is any top-level module programmed onto an FPGA in general must have its inputs and outputs exactly match the corresponding connections between the FPGA and the external components on the board to which the FPGA is connected, or actually soldered. In other words, anything you test on the FPGA, or the virtual FPGA in this case, is limited to having one specific port map on the top-level module, since it represents the top-level module represents a physical device with a specific input and output interface to the outside world. These connections are made using special input and output names and bit widths for the top-level module. Our virtual DE2 board is designed to accept a top-level module from you that has the same named ports as would be required when using the physical DE2 115. In other words, you could take any design that works on the virtual DE2 board and bring it to the lab and run it on the physical DE2 board. These inputs and outputs specifically are 50 megahertz clock inputs named clock_50, clock2_50, and clock3_50. In this class, we'll only be using the clock_50 clock. There are 4 active low buttons that come in as a single 4-bit input signal name key. Now, Charles designed the simulator to actually have those buttons be active high instead of active low. So that's one minor difference between the virtual and the physical DE2 board that you would have to adjust when running your code on a physical board. But that's simple. It just involves complementing the key signal. There are 18 active high red LEDs that go out as a single 18-bit output signal named LED-R, and there are 8 active high green LEDs as a single 8-bit output signal named LED-G. And actually, there are 9 LED-Gs, but on the physical board, the 9th LED-G, the 9th green LED, is not with the other 8. It's located in another spot on the board in between the hex displays. So normally in this class, we only use the least significant 8 green LEDs. There are 18 input switches that come in as a single 18-bit input signal named SW, and 8 separate active low 7-segment LEDs, 7 bits each, named hex 7, hex 6, hex 5, hex 4, hex 3, hex 2, hex 1, and hex 0. Each of these uses the bit to segment mapping shown here. Again, when testing your designs with a virtual DE2-115, your top-level module must conform to the standard input and output signals required by the board. Otherwise, it won't work on the virtual board. This is a limitation because, for example, if you're testing your 32-bit ALU, it would be ideal if you could provide, through the physical inputs on the board, 2 32-bit inputs to the ALU to test, as well as a 4-bit ALU operation code and any other inputs needed. But there's only 18 switches. So there's no way to directly interface with with all the input bits for the ALU through the standard inputs on the DE2-115 board. However, since this is a virtual board, Charles has included a feature called probes that allows you to monitor input signals, and at some point we'll probably add a way to drive in arbitrary internal signals as well. So we would have probes and sources, but currently that is not supported. Now, in order to use both Modelsim and the virtual DE2-115 board, you need to set up a virtual lab workstation on your personal computer that will include all the software you'll need for both of these testing approaches. To do this, you'll need to download a virtual machine image from the Moodle site for the course. This is a large 3.5 gigabyte download, so be prepared to wait a while to pull that down. You also need to download Oracle VirtualBox, which is a free virtual machine software. And once you install the virtual machine, you'll need to do 2 things to set up Modelsim and the virtual DE2-115. You only need to do each of these one time. So after you log in to your account on the virtual machine, the first thing you'll need to do is edit your account's .bashrc file in the home directory and add the following line here. Next, you'll need to open a terminal and type the following command here. With that, I'll allow Charles to explain how to set up VirtualBox and provide a brief tutorial of the virtual DE2-115 board. When Charles is done, I'll be back to do my own tutorial of the virtual DE2-115 board.
Hello and welcome everyone, I'm Charles, and in this video I'm going to talk to you about how to get your virtual machine set up to do your CSCE 611 coursework. So you'll want to have this file, csce611.ova, that will make available to you probably via like a Google Drive link in Moodle or something like that. We'll figure it out. I've already got this downloaded here. You'll also want to already have VirtualBox installed before you go through this video. There's lots of tutorials on the internet for how to do that. You can run it on Windows, Mac, and Linux, and probably other stuff too. But if you have any trouble getting that running, let us know and we can help you get that figured out. But you will definitely need that. So I'll go ahead and open up VirtualBox. And then what you're going to do is you're going to say File, Import Appliance, Source is Local File System, and for the file, you can just select wherever it is that you had it saved. we'll say next, and in here you can change the name, number of CPUs, amount of RAM, etc. You shouldn't need to change any of this though, unless you have a reason that you want to. So there shouldn't be any trouble there, hopefully. And then when you're done, you can hit import. I'm not going to hit import because I've already imported this. It takes it about 5 to 10 minutes, so I don't want to take up too much time in the video doing that. So you should just click import. It'll show a little progress bar, and then it'll be done, and it'll show up. And so I've got that here already running. I've also booted up the VM already, just again to save a little time. But you can click on a VM that's turned off and hit start, and then it'll boot right up. So this is what you'll see when you boot the VM up. So it's kind of just a pretty basic desktop type of thing. There's a README here you might want to check out. The main thing to note is the password for the CSCE 611 user is CSCE 611, if anything prompts you for that. But yeah, we've already set it up. It's got all of the tools and everything you'll need for this class, so you can do all the projects for this class completely in this VM. You don't even need internet access. You can install more stuff if you want to. It's got VS Code, Vim, and Emacs installed already. But if you want to install like Sublime or something, go for it. Whatever text editor you want to use, it's all good. We didn't want to bloat the VM too much with lots of different stuff. And if you don't have opinions on text editors, I'm gonna use Visual Studio Code in this video. And that's what we'll recommend you to use. You'll find it works a lot better than gedit, but it's pretty easy to pick up. But there's no requirement for this class to use any specific one. So now another important consideration is how do you get code into the VM and out of the VM and stuff. There's lots of ways to do that. I talk about some of them in the README. You could use SSHFS, or you could use rsync, or you could have like a Samba server somewhere, or whatever you want to do. It's all good. What I'm going to recommend you to do, though, is to just use VirtualBox shared folders. Those are pretty easy to use and set up, and and don't require as much special knowledge as the other methods. So I'll just go in here to Devices, and I'll go to Shared Folders, and then I'm going to hit Add here, and I'm going to hit Other, and we'll just pick my source folder because that's where my CSCE 611 stuff is. I'm going to say auto mount so that the virtual machine mounts that automatically. You could set a custom mount point, and if you're going to stick with this all semester, you might want to make permanent because otherwise this will go away after the next time you reboot the virtual machine. So I'll hit OK. And now if we open up a terminal in the virtual machine here, and I do df, we can see that it's mounted on /media/sf source in the VM. So I'm going to go ahead and actually open up Visual Studio Code. So we'll do that. And I had actually already opened this, so I'm actually going to close it so that I can, I don't know how you close it, but in any case, you say File, Open Folder, and then you can go into Media, SF Source, and then I'll pick CSCE 611 Labs, Lab Hex, and that'll be the first lab that we're planning to assign. And so now you can see all these files open here on the left. The README will be kind of the lab sheet. We'll probably also put a PDF of that up on Moodle. Definitely make sure you have a look at that. Kind of the rest of the files in here I'm not going to talk about too much in this video, but there will be a handout about like what all of them are and how they work, and if there's stuff there are a couple you will need to change later on in the class, and we'll talk about that later. But for now, just kind of take it as it is. Kind of the main thing is that there's a makefile in here. Hopefully, even if you haven't written a makefile, you're familiar with it. You won't need to change this one, but this kind of automates all of the different stuff that you'll need to do as far as the tools for this class. But let's go ahead and jump in and just kind of make sure that the tools are actually working and that everything's all set up. So I'm going to say New Terminal. This is a really nice feature of VS Code, I think, is that you can just have a nice terminal right here in the window. And so you'll see it's the same files as over here, and this is kind of more or less what you'll see when you download the project skeleton for the first lab. It might change a tiny bit because we haven't 100% finalized it, but it should be pretty much the same as what you're seeing here. So what I'm going to do is I'm just going to type make GUI. So make is invoking make, and then the GUI is invoking a specific target in this make file. Like I said, you don't need to worry too much about how it works if you're not familiar with make. You won't have to edit that file or anything. And there are a couple different make targets. So GUI is what you call a make target, and there's several different ones. So there's make GUI will show this GUI, make test bench will run your test bench, make waves will let you see a GTK wave trace of your simulation, and there's some other ones. That'll all be discussed later though, so don't sweat too much about it right now. So now I've got this GUI booted up. You can click stuff, but like it's not gonna do a whole lot because looks like it has a couple things in there that are kind of stale from when I was playing with it earlier. But when you see it, actually, let me do a make clean. Trouble with these shared folders is sometimes make gets confused on the file timestamps, and you end up with a build that's got half object files from one version of your code and half from another. So if you suspect that might have happened, or you're seeing any kind of stuff where your project isn't acting in the way your code belies it should, maybe do a make clean just to be safe. It only takes a couple seconds, so you can do it every time you run your code if you want. Yeah, so you notice it took a little bit longer after I did the clean, so there was clearly some kind of stale object file in there. Yeah, so now you'll see kind of nothing's happening, and this is exactly what you'll see the first time you run this if you haven't added any code. Right, and this is kind of what you would see if you had a real physical DE2-115 board, since there'd be no code on it, so it's kind of just sitting there as a blank slate, so you can click the buttons and do the stuff and kind of nothing's going to happen, and that's good. That means if you see this and this is how it's acting, then that means your tools are set up and you're ready to go and you can start working on this class. Another thing we can do just to check and make sure everything's set up right is I'll take make test bench, and that's actually going to run a Modelsim test bench for us here. And again, this will just make sure that Modelsim is working properly. We, of course, don't have one yet because we haven't written it, so it's essentially just running a simulation of doing nothing. But it has done nothing successfully, and so that's important. It has 0 errors. If there were errors, then that would maybe mean there was some issue with the tools. So that's really good. That's what we want to see. So I'm not going to walk you through the whole lab or whatever, but I will show you just kind of how to get started. So this RTL folder is where you'll write most of your code for this class. And there's 2 files in here. This simtop, for every project in this class, you will always have a file called simtop.sv, and it needs to have this exact module line that you see right here. It has to stay the same, otherwise the simulator will get confused and it won't know how to get data from your code into the GUI, and you'll have a bad time. So don't change that, but you can put some code right in here. I've been playing with a little bit, but there was a comment here that says your code here, and that should be there in the version that you get. And so all that I'm going to do is I'll just say assign LEDR equals, let's see, the red LEDs are 18 bits wide, so I'll say 18 apostrophe H 1234. And so that should show OX1234 on the red LEDs. And now I'm going to say make clean GUI. So you can do multiple targets when you call make, and so it'll do them kind of left to right, so it'll do clean first and then it'll do GUI. So that's kind of a convenient shortcut. So we will do that. While that's working on that, we'll also look over here at hex decoder. This is the main kind of module that you're writing for this lab. You can delete hexdecoder.sv, you can rename it, you can make other modules in here, whatever way you want to do, it's all good. As long as the simtop is kind of there and set up the way that we set it up, everything else is kind of up to you. But I kind of left this template here because I thought it might be helpful. But you can delete it if you want and do your own. So we've got the simulation here. We'll tick it forward one. Because remember, even though you go, well, as soon as it boots up, shouldn't it kind of, there's not like a clock going on. Shouldn't that value go into the LEDs immediately? And well, technically yes, but this is a simulation. It's not perfect. It can't simulate an infinitely short amount of time. So you have to tick it forward by one simulation step. But you'll see, if I keep ticking, nothing, I can go a couple hundred cycles in the future and kind of nothing happens. So it's just sitting here, and we can see that it is OX1234 that is showing up here. And if you look at the LEDs, they're binary, but if you decode that, you'll see that is in fact OX1234. And this is just kind of a nice feature we put in the GUI, because on the physical hardware boards, of course, you just have the LEDs, and they're just binary, so you've got to decode them. And so anyway, so that's nice. So we can just close out of this. But kind of if you can do that, that's kind of a good way to make sure that you've kind of got the whole tool chain working and you know how to edit your code and stuff like that. So I would really suggest following along with that, just that little basic exercise. As far as the actual code that you're going to write for your assignment, we will discuss that elsewhere, probably in another video. So I think that concludes everything we need to know as far as how to get your VM set up and make sure all your tools are working and kind of things of that sort. One tip I will give you is that if you go File, Close on your VM, you can save the state instead of powering it off, and that way you don't have to wait on it to boot up when you start it again. So you might want to do that. And then, yeah, presumably if you're using some method other than VirtualBox shared folders to get your code in and out of the virtual machine, presumably you know how to get your code out to submit it or whatever as you need. So I think that concludes this video.
Okay, I'm going to show you a quick tutorial on using the virtual DE2 as well as testing with another tutorial on testing with Modelsim and test benches. So I've downloaded the lab 1 rather skeleton on the virtual machine, and I've gone into that directory. Inside here, you'll notice that there are directories for RTL script support and test bench. We'll go into the RTL directory. Inside here, you'll see there's a hexdecoder.sv and a simtop.sv. If we open the simtop.sv, you'll see that the top level input output signals are already given. Be sure that you don't change these in the simtop or the top level design. You can have whatever inputs and outputs you have on any module instantiated under this module, but for the top level module, you want to make sure that you use these same names, signal names, input output signal names. So, so in this demo, I would like to do something with the hex displays and the LEDs. For the hex displays, I want to show one segment lit up and have it rotate around the outer edges of all the segments, of all the 7 segment displays, in a clockwise motion. And for the LEDs, I'd like to basically have one LED on and have it be shifted to the left over and over again. So, I'm going to begin by declaring some signals. I'm going to take all the hex segments. So there's 8 hex displays, 7 segments each. So there's 56 bits there. I'm going to combine them all together into one 56-bit signal. So I'll declare 55 down to 0. Signal here called hexes, and the same thing with the LEDs. I'll declare, so I've got 18 red LEDs and 8, well technically 9 green LEDs, but I only want to use 8 of them. So 18 plus 8, 26, so 25 down to 0 LEDs. And then I'll have these both controlled. Well, first of all, I'll assign hex 7 to be hexes. I'm going to use the bracket here to extract out bits 55 down to 49, which would be the leftmost or most significant 7 bits there. And then I'll do that with 6, 5, 4, 3, 2, 1, 0. And then for the LEDs, I'll assign LED R, all the bits, and LED G, bits, just the bits 7 down to 0. I'll assign that to LEDs, and then I'll go ahead and just assign LED G bit 8, which is the 9th LED G, 9th green LED. I just assign that to 0. So I don't see any high impedance signals in there. And so then I need an always flip-flop block, which I'll use to control these outputs. And that will be activated on pause edge clock 50, as well as pause edge key 0. Now note that in the physical DE2-115 board, the keys are active low, which means when you push them, they're 0. When you release them, they're 1. Charles decided to make them active high, so when you push them, they're 1, and when you release them, they're 0. Not a big deal. You can easily, change the polarity of that if you wanted to port this to the physical DE2 board. Okay, so we'll have a begin and an end for the always. Okay, so the first thing we need to do is handle the reset condition. So if key of 0 is asserted, then there's two things we want to do here. We want to set the hexes to basically have the least significant bit set to 0 and all the other bits set to 1, which will turn off all the hexes except for segment 0, which is the top segment on hex 0. So for that, we use the duplication and the concatenation operator. So left brace, another left brace, 55, 1 bits duplicated, then concatenated with a 0 bit, which will turn on the top segment of hex 0. And likewise with the LEDs, we'll turn on just the least significant bit, which is the rightmost bit there. And then we'll end that, and then we'll say else begin and end. And so with the LEDs, we're shifting the LED to the left, so once it reaches the left side, which would mean that LEDs of 25 is turned on, then we want to wrap that over to the right side, back, basically wrap it back to from the left-hand side back to the right-hand side, because we're shifting to the left. So that would be LEDs 0 would then get assigned to 1. Now, I just noticed I made a mistake. I want to make this is sequential logic, so I should be using non-blocking assignment statements here. Make sure you do that for sequential logic, especially in this example. And if you make a mistake and mix blocking and non-blocking, then you'll get a compiler error with Verilator, but not with Modelsim. Okay, so now we have the special case where the LED gets shifted off the left-hand side, goes back to the right. But under normal circumstances, LEDs will just be shifted right by 1 bit. So that's done. Now, as for the hexes, it's a little bit more difficult. So we need to have a special, basically an if statement for each hex segment that's lit up to determine where it goes next. We could use a case here. I'm going to use an if statement. So I'm going to say if hexes, I'm going to look at the old state. Now, first of all, before I do that, I need a default value. So by default, the hexes will actually be 56 1 bits. So they'll all be turned off by default. And then I'll change whichever one I want to change. Now notice that this is a non-blocking assignment. So in the if statement that follows that assignment, the if statement will act as though I had never set that hexes to all 1s. It'll assume that hexes is whatever it was set after the last activation. Because with a non-blocking assignment, the assignment doesn't take effect immediately. It takes effect after the always statement has completely run, and any assignments that do take effect are the last assignments to take effect. The ones at the bottom, the ones that happen latest. So by assigning everything to 1, it allows me to have a default for the next state of all the hex bits, and obviously change individual ones as I see fit. So now if hexes, let's start with the sort of the default case, which is hex 0, which is the least significant bit of hexes, which is the top segment of the rightmost hex. Now I'm going to do a trick here with the addressing. I am going to address it by saying the hex number times 7 plus the segment number. So I'm basically going to do kind of array-based, row major array style addressing here just to simplify the readability. This sub expression here, 0 times 7 plus 0, obviously evaluates to 0, and so the compiler will just convert that to 0. But it's not going to generate any hardware to do that multiply. So since there's just constants involved, but this will make it easier for me to read. So basically, what this is saying is that, and I'm going to put a tilde here because these are active low. So if the least significant bit of hex 0 is turned on, then I want to since I'm going clockwise, I want to light up the upper right-hand segment of that same hex. So I'll just say hex is 0, hex 0, okay, segment 1, which is the upper right-hand corner segment. I'll assign that to 0, which will turn it on. And then I'm going to add a bunch more of these here. So then the next after that, in other words, if, sorry, I changed the wrong, let's see, I want to change segment 1, hex 0, if that's turned on, which it will be in the second clock cycle after this thing starts going, then I'm going to turn on segment 2, which is the lower right-hand corner segment. And if that segment is on, then I'm going to turn on the bottom segment, which is 3. And if that bottom segment is on, then I'm actually going to jump over to hex 1 bottom segment. And if hex 1 bottom segment is on, then I'm going to jump over to hex 2 bottom segment. And if hex 2 bottom segment is on, then I'm going to jump to hex 3 bottom segment. And if hex 3 bottom segment is on, I jump to hex 4 bottom segment. So this is me working my way from right to left along the bottom row of segments. Let's see, this would be 4 is on, then I'm going to jump to 5, and if 5 is on, let's see, 3, I'm going to jump to 6, and if 6 is lit up, segment 6, or hex 6, segment 3, then I'm going to jump to 7. Okay, now I've worked my way over to the left-hand side, and so I need to work my way up the corner now. So if I'm on segment 7, hex 7, segment 3, then I'm going to work my way up to the lower left-hand corner, which would be hex 7, segment 4, and then hex 7, segment 5 will be the upper left-hand corner, and then once I get there, then I'm going to go to the top on there, which is segment 0, because segment 6 is the middle segment. So now I've gone around the corner, and I'm back to the top. Now that I'm to the top, I can... and I need to make sure I change these to segment 7. Now that I'm to the top segment lit up on segment 7, I need to work my way from left to right along the top row of segments, and that would be segment 0. So I'm going to copy this a bunch of times, and so now I find myself here at let's see, segment 7. Hex 7, segment 0. So now I'm going to go to 6, segment 0, and if I am on 6, segment 0, then I will go to 5, segment 0, and if I'm on 5, segment 0, I'm going to go to 4, segment 0, and if I'm on 4, segment 0, I'm going to go to 3, segment 0, and if I'm on 3, segment 0, I'm going to go to 2, segment 0, and if I'm on 2, segment 0, I will go to 1, segment 0, and if I'm on 1, segment 0, then I will go to 0, segment 0. Okay, now at this point, I believe I'm done because hex 0, segment 0 is where I will then repeat this cycle. So there should be 20 segments in total. There's 8 on the bottom, 8 on the top, that gives me 16, and then 2 on each side, that gives me 20. So let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. There we go, we got 20 if statements, so that makes sense. Yeah, that should be it. So I'll go ahead and save that. I'll compile that just to see if there's any errors that Modelsim reports. There are none. So in order to test this in Modelsim, I'll write a quick test bench. This will be easy because I'm just going to visually validate it with the waveform editor. So I'll create a test bench.sv. So the module test bench. And don't forget the semicolon and module. Then I will declare some things like clock and let's see, 3 down to 0, key. I'll just use lowercase here. And logic, let's see, 17 down to 0 would be my LED G. And 8 down to 0 would be my LED R. And let's see, I've got 6 down to 0 for hex, hex 0, and hex 1, hex 2, hex 3, hex 4, hex 5, hex 6, and hex 7. 0, 1, 2, 3, 4, 5, 6, 7. And then I think that's all I need. And so I will go ahead and say simtop dot. And so it's got clock 50, which I'll tie to clock. And let's see, clock 2, 50 will also be connected to clock, and clock 3, 50 will also be tied to clock. So my clock's going to fan out to all 3 clocks. And we have LED G, which is LED G, and dot LED R, which is my LED R, and finally key, which is my key. And I've got finally hex 0, which is hex 0, which is hex 0. And so I need to drive the clock. So always begin, clock equals 1, wait for 5, clock equals 0, wait for 5, and then let's see, we'll end that, and then we'll have initial begin. We'll set key 0 to 1. We'll wait for 7 units, set key 0 to 0, and then we can end that. So that should be all we need for the test bench. So I'll save that. I will compile that. No warnings. So now we'll simulate the test bench with vSim. I'll maximize the Modelsim window. I will basically drag all the signals into the wave window. And then I'll just run it a little bit here. Okay, well, I see some stuff happening here. That's good. I think I see a problem, though, with the LEDs. So I can see the hexes appear to be working. So I can see that there's just basically 1, 0 that's sort of propagating around, and around the 7 hexes. That looks good. The LED G, however, is got a bunch of Z's in it, and the LED R is getting shifted, but once it gets shifted off the end, it kind of dies. So there is a problem there. Now LED R, I think I see the problem. I think I switched LED R and G. Sorry. Okay, very good. That's easy to fix. So I'll go over here and I'm going to edit the test bench, and let's see. Yes, LED G is actually 8 down to 0. LED R is 17 down to 0. So that would explain that. Yeah, so let's go ahead and recompile the test bench, go back to Modelsim, and restart and rerun that for a bit. That looks much better. Yep, I can see LEDG, and LED-R running. Now, one thing I just noticed here is it says there are too few port connections for the DUT. Apparently, I forgot a port. So if we look at SimTop, let's see, what am I forgetting here? LEDG-R key, the switch, that's what we forgot. So we can go back in the test bench. Of course, we can add the switches. I didn't use them, so I'm just going to, I could just leave them floating, or I can connect them to, I'll create a signal called SW, which then I can logic 25 down to, 17 down to 0. I believe it's 17 down to 0. Yeah, 17 down to 0, SW, and then I can just assign SW 18V0. Oops, sorry, V0. Okay. And so vlog test bench, that works. Just to double check, the SimTop is the switches are 18 bits. Very good. If I go back to Modelsim, I can go ahead and restart that. That shall pick up my, and I no longer get the error. Okay, so, or the warning rather. So we're good to go. Everything checks out with Modelsim. So now it's time to try the virtual DE2 board. So I'll go up one level and I'll type make GUI. Now, one thing I noticed is that if you make any changes to your RTL and you make GUI, it won't see the updated. It won't see the updates. You need to do a make clean and make GUI. Obviously, I don't have to do a make clean right now because this is the first time I've made it. But I'm just gonna. I'll end up just reusing this command multiple times, so I'm just going to go ahead and add the make clean right now. And so this will, I think the first time you do this, it takes longer than it does on subsequent times.
5 hours later.
Okay, so now we have our virtual DE2 here. And so remember, we have to reset it first. So I'm going to hit the key 0. That should reset. And then I will do some ticks, and then I'll hit that again. And it's a little fussy sometimes. Sorry. It's a little fussy. I'm not sure why, but there it goes. Now we're going. So now you can see the it appears to be working. The segment is rotating on the outer segments. Strangely, though, it appears that the LEDs aren't working the way they're supposed to. So I just realized when running the virtual DE2 that I did have a bug in my SimTop. Basically, and I'm not sure why I didn't notice this in Modelsim, but when I reset the LEDs from the leftmost LED position to the rightmost LED position, instead of just setting bit 0 of the LEDs, I'm going to set LEDs to be 26 with a binary value of 1, much like I did when I initialized it there. So if I try that again, it behaves a little better. Okay, so I'm going to click key 0 and I will tick it a few times, and then I'll click key 0 to turn it back off, and then I'll tick it, and you can see now that it appears to be working better now. That the LED R and G appear to be working well. So that's all for the demo. We'll see you next week.